Okay, let's unpack this. Welcome to the deep dive. Today, our mission is exploring how scientists are supercharging everyday plastics using what is basically an old metalworking trick.
Right. We are extracting insights from a 2026 structural integrity study on ECAE, which is equal channel angular extrusion, applied specifically to polyamide.
Yeah, so imagine forcing a lump of Play-Doh through a sharply bent pipe, right? But without changing the pipe's width at all.
Exactly. For metals, that severe plastic deformation makes them incredibly strong. It's a massive structural boost.
But for plastics, it is a huge challenge, and that is why this study is so cool. I mean, polyamides like nylon are everywhere, replacing metals and gears and electronics because they are so cheap.
They are super versatile, but, earlier attempts to use the CAE process on them just completely failed.
Oh, yeah, I saw that. Because if you use a standard 90-degree pipe angle, it just blocks up, right?
Yeah, a 90-degree angle causes the polymer chains to just bind up entirely. You get massive blockages and, well, total extrusion instability.
Like taking a hairpin turn in a race car and just crashing straight into the wall.
Right, exactly. So then manufacturers tried, widening the angle to 120 degrees to let the material flow easier.
Which makes sense, logically.
It does, and it extruded fine, but the plastic actually warped. It came out way too curved to be structurally useful.
So you are taking the curve too wide and getting no G-force, or I guess like trying to comb out heavily tangled hair, and your comb just glides over the top without actually catching the tangles.
That is a great way to put it. And what's fascinating here is how the researchers engineered a 105-degree die. It's basically the Goldilocks angle.
Ah, right in the middle.
Yeah, it is a perfect compromise. It balances the physical feasibility of actually getting the plastic to flow with effective molecular orientation.
Right, because 105 degrees is the exact sweet spot. It provides just enough resistance to force all those chaotic polymer chains to stretch out and like perfectly align parallel to each other.
Which is exactly what gives the plastic that metal-like strength.
Okay, so once they have that 105-degree channel set, they have to perfect the actual bend itself, right, to make sure the strength is uniform across the piece.
Oh, the inner corner geometry. Yeah, they did.
Here's where it gets really interesting. Wait, looking at the data, they found that a sharp 15-degree inner corner created more uniform plastic strain than a wider 60-degree one. That feels totally counterintuitive.
It really does. You would totally think a wider, softer inner corner would ease the material through, make the stress more even across the whole piece.
Exactly.
But if we connect this to the bigger picture, it makes perfect sense. A sharper 15-degree inner corner forces an intense, sudden molecular realignment all at once.
So it doesn't let the material loosely cheat the turn, essentially.
Right. By forcing that abrupt shift, the study found the strain variation factor dropped to just 19.8%.
Wow. Compared to almost 29% for the 60-degree corner.
Exactly, meaning the plastic wasn't just strong on the outer edges and weak in the middle. It was almost uniformly tough all the way through.
That is wild. So if forcing it through that one sharp bend aligns the molecule so well, does running it through multiple times make it even stronger? Like folding steel in a sword?
Precisely. The study tested exactly that, using a double-turn die. They call it a 2-ECAE setup.
And they used a really short channel between the bends, right? Like 20 millimeters.
Yeah, just 20 millimeters. By forcing the polyamide through that rapid double turn with a 15-degree inner corner, the variation in the plastic strength dropped to an incredible 11.8%.
So it became highly homogeneous.
Extremely homogeneous.
I also saw a note in the research about friction, which, wait, doesn't friction usually ruin extrusion processes?
Usually, yes. You want to avoid it. But they noted that adding a little bit of friction to the channel walls actually increases the intensity of the deformation.
Really? How does that work?
Well, that friction acts almost like a grip. It momentarily holds the outer layer of the plastic back while the inside pushes forward.
Oh, I see, creating a shearing force.
Exactly. A shearing force that further aligns those polymer chains. Though, obviously, too much friction, and you risk breaking the equipment entirely.
Right, nobody wants a broken extruder.
Right.
So what does this all mean for you listening? It means the lightweight plastic gears inside your car or the casing of your next smartphone will possess metal-like durability simply because of the exact mathematical way they were bent during manufacturing.
No extra chemical additives required, just pure geometry.
Just geometry. It is amazing.
It really is, and this raises an important question. If a simple 105-degree bend and a sharp 15-degree inner corner can completely rewrite the structural limits of industrial plastic,
Yeah.
what other everyday materials are hiding superhuman strength, just waiting for the right geometric squeeze?